All right, today we're still going to be modeling, so meaning like word problems. We're still going to have word problems today, but we're going to be looking at our base E functions. So you guys will be able to use base E exponential models in context today. Today's lesson is mainly going to just be calculator work. It's just plugging in a number and then figuring out the answer, basically. All right, so for a concept today, it says what values of bases in exponential functions will produce exponential growth or exponential decay. So this is kind of what we talked about yesterday. So if you remember, for exponential growth, our exponential growth formula looked like what? I'm just going to say like f of t equals, what did our like formula or function look like for exponential growth?
Equals
A times to the t power. Good, that was a growth, right? And then the decay was a f of t equals what? What was the difference between the growth and the decay? The decay had a 1 minus r to the t power. So what type of numbers, when I simplify, were inside the parenthesis here for my base? Was the number greater than 1, less than 1, equal to 1? It's a 1 plus r, so I'm adding to 1. So remember, this one we had like a 1.15 to the t power, for example. So the numbers inside the parentheses, the base, are numbers greater than 1. Would produce an exponential growth. The decay ones, notice I'm doing 1 minus r, so I'm subtracting from 1. So these numbers in the exponential decay were actually like a 0.905, for example, to the t power. And so these numbers inside the parenthesis, our base, are actually numbers smaller than 1. Okay. I verbally talked about it yesterday, but I don't think I explicitly ever like wrote it down. So the exponential growth inside the parentheses, if the number is greater than 1, then that means it's exponential growth. If my base inside the parentheses is less than 1, then that means it's exponential decay. So it's actually getting smaller. So for today, did you need that still? Sorry.
No, I was talking to Joseph.
So for today, we're going to be looking at the irrational number e, and sometimes we call e the natural base, and it's used extensively in scientific and other applications of exponential growth and decay. So e is this number right here, 2.7182881828. So it keeps going on forever. It doesn't end. That's what's called irrational. Kind of similar to pi. You know how pi keeps going on forever and there's no like specific pattern. It's 3.1415926, yada yada yada. It keeps going. Yes. So pi is irrational because it keeps going. There's no pattern to it. So likewise with E is a 2.718281828. It keeps going. Okay. So irrational means a non-repeating, non-terminating number. So we're going to look at functions today that have the base e. So for example, number 1 here, it says the Dow Jones Index is a stock market index for the New York Stock Exchange. The Dow Jones Index for the period 1980 to 2000 can be modeled by this function V of dj for t. And then it tells us that t is the number of years after 1980. So in this case, it says for part A, use a function to estimate the Dow Jones Index in 1989. So I need to figure out what my T is going to be so that I can plug it in to my function here. Because my only variable really that I have is T. E is not a variable, E is a number, and then I have T up here. So the only variable that I have is T. So for part A, I need to figure out what to plug in for T. So the piece of information that I have here is T is the number of years after 1980. So in 1989, how many years have passed after 1980? 9. So 1989 minus 1980 is 9 years. Okay? So all I do is then plug in 9 to my function. So I have V of, I'm just going to put V instead of VDJ. V of 9 is equal to 878 times E to the 0.121 times T, but my T is 9 here. So for today's lesson, basically it's just calculator work. I have to just figure out what's T, plug it in, use a calculator. So to type this in the calculator, you're going to plug it in, put 878, and then to get to the E, you have to do, E is right here above the ln. Do you guys see the E to the x power right there on the ln? So to get to it, you would have to do 878, then you click on second, and then ln, and that should give you the E to the power, and then it opens a parenthesis, correct? So you have the parenthesis, and then you have to plug in the exponent. So my exponent here is the 0.121 times 9. So I have to put 0.121, and then you're going to put times 9, close the parenthesis, and press equals. So this is how you plug it in the calculator. 878, second ln, gets you the E, and then it automatically opens the parentheses, so the exponent is 0.121 times 9, close the parenthesis, and then press equals. So for V of 9, go ahead and compare your calculators with your partner. Did you guys get the same value? Okay. What did you guys get for your answer? Like 2000 something, yes? 608. Okay. Because we're talking about the stock market, that number really is like it's talking about money. So 2,608 with like about 80 cents. Okay. Because this is a context problem, you would want to write a sentence. So we would say in 1989, comma, the Dow Jones Index was about $2,608 with 80 cents. Okay. Part B is pretty much the same, except part B is you're estimating in 1992. So for 1992, what is our T going to be? Go ahead and righties, share with your runner. Righties, what would T be in part B? Remember, t is the number of years after 1980. So 1992, how many years have passed? 12. So my t is going to be 12 in this case. We're going to do 1992 minus 1980. That gives us 12. Okay. All right, so I want you guys to go ahead and plug in 12. I have the calculator right there. Basically, just replace the 9 with the 12. And then see if you can get the answer. So good. If we plug in 12 in the calculator, you should get 3,750 with 51 cents. And then don't forget to write your sentence conclusion. In 1992, the Dow Jones Index was about 3,750 with 51 cents. All right, so moving on now, we're going to go to the next example. So in this next example, we have paleontologists study fossils and can determine their age using the natural decay rate of carbon-14, where the age of fossils is the number of years following the death of the specimen. So the percent of original carbon-14 in a specimen t years after the death of the specimen can be modeled by the function n of t. And it tells us specifically t is the number of years after the specimen died in thousands. Okay, t is in thousands. So in this case, part A, it says determine the percentage of carbon-14 in a specimen that died 15,000 years ago to 3 decimal places. Okay, notice my t is 15,000 years ago is when it died. But 15,000, if I plug in 15,000, it's going to be like a huge number. But here it tells me t is in thousands. So in this case, because t is in thousands, my t is 15,000. So it would just be 15. Okay? Basically, take the 15,000 and divide by 1,000 to get me t. And t is 15 in this case. Okay? So I would plug in then t to my function. I have n of 15 is equal to 100 times e to the, this time I have a negative 0.12 times t, and my t is 15. All right, and then for the calculator, you have to be like careful on the calculator. You want to use the negative, the one that's kind of underneath the 3, the negative. You don't want to use the subtraction symbol. If you use the subtraction symbol, it's going to give you an error message. So you use the negative under the 3, okay? So for your calculator, you're going to plug in 100 second ln, and then it'll automatically open the parentheses. So you want to use the negative button, this button with the negative in the parentheses, and then the 0.12 times 15, close parentheses, press equals. Okay, so 100 second ln, negative 0.12 times 15, close parentheses, press equals. Okay, and it says to round to 3 decimal places. So after the decimal, we need 3 numbers. So what did you guys get in the calculator? 16.529888888. And I keep going. But the direction says to 3 decimal places. So I'm looking at the third number, the 9 right here. That's where I need to round to, but the one next to it is 5 or more, so we have to add one more to the 9, which is 10. So my 29 is going to be really a 30. So it's approximately 16.530. What is this number representing? This is the percent of carbon-14. So this is 16.530% of carbon-14. Okay. And then we have to write a little sentence conclusion here. So we would say a specimen that died 15,000 years ago. A specimen. Sorry, that doesn't look very good. So a specimen that died 15,000 years ago would have about 16.530% of carbon-14. All right, so for part B here, I want you guys to try this one. It says determine the percentage of carbon-14 if the specimen died 10,500 years ago, and you were rounding to 3 decimal places. So 10,500, I need to figure out what's my t going to be. So remember, you can do 10,500 divide by 1,000 to figure out what t is going to be. So go ahead and lefty to your partner, what are we going to use for t? You guys are very quiet today. You guys aren't talking. Are you guys confused? You're just to figure out what t is? Because t is in thousands, right? So you would divide your 10,500 years by 1,000 to get your t. That's just the natural, that's just the base e. That's what we're learning about today. So does anybody know what to do for t? What are we going to plug in? 10.5. Okay. All right, so I want you guys go ahead and plug in 10.5 and see if you can get the answer. All right, so again, in this case, our t, 10,500, if you divide it by 1,000, you should have got 10.5. And if we plug in 10.5, on the calculator, you do 100 second ln to get to e. You need the negative symbol, 0.12 times 10.5. Press equals, and you get 28.365. So that's how much percent of carbon-14 there would be if the specimen died 10,500 years ago. All right, so we're going to skip the next practice problem just because I'd rather have extra time at the end to work on the assignment. And instead, we're going to do the next example. So we're going to skip one and then go find this one with the sodium 22. So here it says the amount of sodium 22 present at the time t in years can be modeled by the function s of t here. So notice for s of t, I have an a this time times e to the negative 0.267 times t. And do you guys remember what a standard for yesterday in our functions? What did A stand for? Yes, it's the specifically it's the initial value, right? So A was the initial value.
Is it always going to be the initial value?
Yes. So in this case, it says if 300 grams of sodium 22 was present in a soil sample in the year 2010, how much sodium 22 will remain in the year 2020? This was around to 3 decimal places. So in this case, what's my initial amount of sodium 22? What is it? The initial amount of sodium 22.
300 grams?
300 for the year 2010.
Yes.
Okay? So A is 300 for the year like 2010. So I'm going to go plug in A to my function S of t to create my equation or function. I have S of t is equal to A, but A in this case is 300 times e to the negative 0.267 times t. Okay? All right, then it goes on to say how much would remain in the year 2020. So because I'm starting in 2010, how many years have gone by for the year 2020? 10, good. T would be the from 2020. But I had initial year of 2010. So from 2010 to 2020.
Where do you get 0.267?
That's just the function that's given to find the amount of sodium present. Like I didn't make that was just in the function.
Oh.
That's right here in the function.
Okay.
So all I need to figure out is what's t. So my t in this case was 10. So now I'm going to go plug in 10 for t. So my function is s of 10 is equal to 300 times e to the negative 0.267 times t, which is 10. Okay, so grab your calculator and then go plug that in for 10. And then tell me what you get for your answer. Okay, again, so for your calculator, you're going to plug in 300, then second ln, and then click on the negative symbol, 0.267, and then you're going to go times 10, close the parenthesis, and press equals. 20? Did you guys get that? 20.775? Yes? Okay. So 20.775. Okay, good, because it does say around to 3 decimal places. So good. So then you would write a sentence. You would say in 2020, there would be about 20.775 grams of sodium 22 remaining.
Camry.
All right. So in this case, whenever you have something with an A in there, you have to figure out, just remember A is the initial value. So in this case, we had originally 300 grams of sodium 22, and then you just plug that in for A, figure out what the T is, and then plug it in. Okay. All right. I am going to go ahead and stop the lesson there. I'm going to skip the practice problem because I'd rather give you guys time to do the assignment in class. So rest of the period, you guys are working on the 9-2 assignment, which should be the next page over. Okay.